My name's Brenda Rosser. I'm a geomorphologist at GNS Science, and I'm going to be talking about mapping landslides. So just a little outline of my talk. I'm going to talk a little bit about the data and imagery sources available for mapping landslides, a little bit about identifying them in the field, identifying them in imagery, so both manual and semi-automated, and mapping landslides in GIS, and then a little brief bit on some landslide susceptibility models and hazard mapping. So a little bit about me. I did a Bachelor's in Earth Science at Massey a long time ago, and then in fluvial geomorphology at Massey. I worked for about 25 years at Manaaki Whenua Land Care Research with Chris, and so yeah, I did 8 years consulting in California, and I've been at GNS Science for 12 years, where I'm a engineering geomorphologist. So I've been mapping landslides for most of my life. I started when I was about 13 on Cyclone Bowler, and then it's in 1988 for you young ones who were even before then. So I learnt from the experts, Noel Trustram, Mike Page, Mike Martin, Chris Phillips, the gang from Land Care Research, and it was DSIR back when I started. So I've been, so I've mapped landslides from the Christchurch earthquakes, the Kaikoura earthquakes, Cyclone Gita, and at the moment I'm heavily buried in mapping from Cyclone Gabrielle. So why are landslides an issue in New Zealand? So they're our most common natural hazard, and they most commonly affect property and infrastructure. They cost the economy a lot of money. This is a bit of an old estimate at the moment, so at least $250–300 million per year, but we're hearing that Cyclone Gabrielle's costing up around $8 billion perhaps, but that's including both landslides and flooding. And they kill about, since the beginning of our records, which is about 1760, there's been about nearly 800 deaths caused by landslides, compared to 450 by earthquakes. So landslides are pretty important. So why do we need to map landslides? Just with Cyclone Gabrielle alone, we've mapped over 150,000 landslides so far. So we need to know where those landslides are so that people can plan and prepare, but also we can get a lot of information from where we map those landslides. So when you map the landslide, you know the location on the landscape, where it is, all those underlying factors that control landslide susceptibility, and if it's related to a specific event, like a triggering event, like an earthquake or a storm, you also know what triggered that landslide. So the rainfall that triggered it and the soil moisture conditions at that time. And so then we can use that information to build models and predictive models to try and predict where those landslides are going to occur in the future. So this is just a big horrible list of websites and stuff where you can get, so this is the underpinning data, so data that would be included in a landslide susceptibility assessment. These are the things, so like I'm sure you guys are all aware of these sites probably already, but the NZARM, the land cover database, and then at NBF we've got the river environment classification, rainfall, highly erodible land, and then LINS data service, with the aerial photography, LiDAR, digital elevation models, soils and geology, and then erosion. We've got NZLRI, got potential and current erosion included in NZLRI, and then there's a couple of data sets that are derived from the NZLRI, so the erosion terrains from Manaaki Whenua, and also highly erodible land. So these can also be used to sort of like identify the underlying physical properties of the landscape. And If we're looking at storms, which seem to be a lot lately, there's really useful information, rainfall data from the VCSM, which is the Virtual Climate Station Network from NIWA. So you can get rainfall information and from the previous day, but also you can go back in time and get rainfall information. There's the HIRDS, which is the high intensity rainfall design system. So that's when we can look at your 100-year rainfall event, see what and how the rainfall changes for different return period events. And also with HIRDS, really important now is the climate change predictions. So you can add those in and get the rainfall predictions for different scenarios. And most of these data sets are available via ArcGIS online as well. So some of the imagery, when mapping landslides, the imagery is really important. So the source of the photography, we can get that from lens, retro lens, or WSP. And then the base maps and ArcGIS. Did most of you guys use Arc?
Yeah.
And then satellite imagery, Sentinel, Planet, or SkySat. So Sentinel is the 10 metre, Planet's the 3 metre, and SkySat is 0.8 metre. And most of the time we get the LiDAR from LIDARs or from the regional councils. And most of you guys use LiDAR for everything? For mapping?
Starting to be really.
So a little bit about identifying landslides in the field. So there's lots of things that you can look for in the landscape. I'm sure you guys are already doing this already. I feel like I'm like talking to the computer. But so these are the things we're looking for. One's the cracks, sketching cracks, leaning trees. This is a anti-scarp, so it's leaning backwards as well. What else we got there? The intention cracks. Oh, sorry, scarps. This is actually all from one landslide, the TRI landslide up at Gisborne, from one nice day out of the field. Got wet areas, ponds, anti-scarps so scarp is when it's when the legs drop down. They're sort of like they're tilted back rather than tilted forwards. So that it did not very clear. Yeah. So and then hummocky ground. You can see this this ground in here is not nice and smooth like the areas on either side. Fallen trees. There's another nice scarp alongside there. You can see that this ground here is a lot smoother than the uneroded slope out here, and you can see these wet areas with the reeds. So there's all sort of like giveaways that there's actually a landslide there. So hummocky ground. Some more here, you can see this is where the debris is moving with this area here. This is the hummocky ground where the material is moving down the slope. And you can see this from the air as well. So this is the bit that's moving or moved in the past. This is just, here's some of our reeds, and you can see the scarp running along here. I just put the line in there. That's the outline of the source area. And then we've got incipient landslides. So these are landslides that nearly failed. So these were taken in after Cyclone Gabrielle up in Gisborne. So you can see there's areas here where there's cracking. So there's cracks, and there's cracks all over here. And you can see over here, this one here that's bulging, is bulging down here. So this is a slide that's not quite, hasn't quite initiated. It hasn't quite, it's initiated, but it hasn't quite moved. It's all sort of sitting on the landscape, but there was a lot of these after Cyclone Gabrielle, and we think that these are going to be reactivated in upcoming storm events because it's already a landslide there, but it's just not quite, hasn't evacuated all the material from here. And this is another one here. These ones actually failed in the lower part of the slope, but so you can see this cracking up around the top here. So this sort of indicates that there could be a slide plane underneath there, that these then move down in previous storms. In storms following storms. So identifying landslides in imagery. So first of all, using manual interpretation, so just visual interpretation, looking at pre and post event imagery. So this is aerial photography. So this is a pre image, and this is a post image of the same area. So this is a Tiniroto near Gisborne following Cyclone Gabrielle. So those landslides are pretty obvious. And then you can use semi-automated processes like satellite imagery differencing. So with Sentinel and other satellite imagery, you can just take the red band. The vegetation is reflected as sort of different levels of reflectance, I suppose. If you take before and after, hang on, this one shows it a bit better. This is Kiowa near Gisborne. So this is before the March 22 storm event. So you can see the bright areas here is where there's really healthy vegetation. There's dark, the red is still vegetation, but and then following the storm, you can see with the landslides there, that's really high reflectance, the brown bits there. And you can just add the red band in ArcGIS. You can, when you double click on a raster image, it splits it into red, green and blue. You can just add the red band, and then you can subtract one from the other and get the difference between the two before and after, and that highlights where there was vegetation and now there's not. And then you can classify that so that it shows those only those areas that were vegetated before and now they're not, so it's probably a landslide. So
question back here.
Sorry, I'm just curious, why are all the landslides on the north faces?
Probably because the storm came in from that direction. And yeah, I'm pretty sure, I don't think there's any difference in the slopes on either side of those hillsides, but I'm pretty sure it's just what direction the storm came in, so what side of the hill slope the rain hit. So these slopes will be in the lee side, so they would get less rain.
Coastal too.
Yeah.
You've got the extra erosion.
Yep.
Coming straight off the coast.
Yeah, sure. So I just wanted to show the difference in image resolution. So it's really important to have the best imagery that you can get. And I'm really old school, so I really like aerial photography. Can't be aerial photography because we can get the resolution down to about 0.2 meters, and you can see how crystal clear that is. And then planet imagery, same location, that's 3 meter resolution. And then this is Sentinel imagery, which is free, but it's 10 meter. So you can see that it just turns into a big blob, and it's really hard to differentiate between all these slips. So that's, yeah, you can still see that there was landslides there, but you can't differentiate it into the individual landslides.
Do you use the retro lens?
Yeah. Yep. So retro lens is good for historic aerial photos. Yeah. So yeah, I've used that many times. But I think you have to actually, when you get the photography from RetroLens, you have to rectify it yourself, eh? Yeah. Which means put it into like geospatial reference.
What about photo oblique? Have you used that tool?
No, I haven't.
It's pretty cool. Northland and Waikato and Bay of Plenty have it now, where there's 45-degree images from a plane at 500 metre or 1 kilometre centres. And
Is that, so that's from a plane, not a satellite?
from a plane, and we get it done every year for like 130 grand.
Yeah.
So it's absolutely amazing. We use it for wetland delineation, and you can drape over 2D shapes on it as well.
Yeah, that sounds great. I'll have to look that up when I get back. So this just shows the process with the red band different things. So when you add just the red band by itself, it's just black and white, and you can see this is Cyclone Gita down in Nelson, Tasman area. You can see this is the pre-event, and then the post-event you can see the landslides showing up as these white areas here, and then subtract the post-event from the pre-event, and you can look at the differences. You have to sort of classify it a little bit so that you can pick out those changes, but then you can classify it and then put a really horrible colour scheme in so that it shows up the areas of the biggest change, and then you can identify them as being landslides, and then you can actually, so if you classify them, and then you can turn them into polygons in ArcGIS. So this is the same area, and then there's quite a bit of checking and like further classifying them in to different. So this is classified into landslide source areas, actually sources and deposits, and then these are the overbank deposits downstream. So these were from debris flows in Cyclone Gita. So with satellite imagery, it's really hard to separate the landslides into source and deposit, because the course of the resolution of the imagery, the less detail you have, and we can't see the details on the ground. And I'll show you some of that a bit later. So this is just an example from Cyclone Gabriel. We were sent a whole lot of automatically classified images and mapping products from NASA and all sorts of people around the world, using mostly the 10 metre Sentinel imagery. So they've taken the best image that they can, but still, it still requires a lot of interpretation. There's a lot of false positives, and you can see the blue areas here are the polygons that are derived from that automatic classification from the Sentinel differencing, and the red dots are the manually mapped points. So you can see that there's like this polygon here has got, I don't know how many dots in there, 7 points within that one polygon. So we're not counting landslides properly that way. We can identify bare ground, but we can't identify individual landslides and parts of a landslide. Then this is just another example. So the red areas here are what was automatically classified using the Sentinel differencing, and the red, so the circles are manually mapped landslides. The green ones are the ones that were picked up or pretty close to the Sentinel polygons, but the red ones were completely missed by the Sentinel differencing. And I think it was about a third of the landslides were missed, and it was most of the smaller ones actually. And you can see this one here would be counted as 1, where there's about 10 landslides in that area there. So when we're mapping landslides, these are the sort of the main things we try and capture. So the source area, where the material comes from, and the deposit, where it ends up. And yeah, so normally do that with, I hope I don't really have time to go into like GIS processes of mapping here, but basically what we want to do is have a feature class where we can separate out the source area from the deposit. And we also want to record attributes about the landslide, so the type of landslide, the materials, whether it was new, whether it was there before, whether it's connected to a stream, those sorts of things, and sort of what's important for you when you're mapping those landslides. What information do you need to get out of it? And we can use that using points, lines, and polygons, or a mixture of points and lines. So these are just your typical landslide features. So yeah, the main ones we're sort of interested in are just, as I said before, the source area and the deposit, and often the deposit is not completely removed. So this would be mapped as deposit up here, it's still sitting there on the landscape, and there's quite often an overlap between where the material came from, and then some of the deposit's still left sitting there, and then the deposit going down the hill here, and you can see this in this one here. So the source area would be this whole area here, I think, right down to the stream, and then the deposit's still hanging up there on the slope. And these deposits are pretty vulnerable, susceptible to landslide, to coming down and following storm events.
So that would just keep could you fix that?
I don't think so. It's pretty big. This is a pretty big one. I don't think you could fix it.
So it'll just keep dropping down?
Yeah, because there's a slide plane under there, and that you can see all these cracks, tension cracks and all that. That means that is, moving.
Yeah.
And if we took some photos, at different times after this, we'd probably see that this is moving slowly down the hill. Yeah, I mean, you could get in there and plant it up, but don't know how much good that would do. Chris is shaking his head. No.
Just a question. Where would you put, if you were mapping points, where would you put the point of that landslide on that particular
Yeah, okay. So how we're doing it at the moment is that we are putting a point in the middle, centre of the source, and I'm going to get to this bit later, but and then we scale the point to the size of the landslide. So that the point represents the source area where the landslide came from. Because when we're developing our susceptibility models and predictive models, we want to know the properties and the information about the area where the landslide was triggered. So, and then we can look at the deposits separately. So the run out, how far did that run down the slope? We have to do that separately because that's a different process. So this is what we do with points. This is the easiest and quickest way to map landslides, but we don't get a lot of information. So we normally put it in the centre of the source area. You can record attributes. I don't know why I put that up there. It's really quick and easy, and you can just fly over an area really fast to get like just a quick ballpark estimate of how many landslides are in an area, but you don't get any information about the size or the type or anything like that. Run out. And then you can use points and lines, which are oriented polylines. So this is what we're doing for Cyclone Gabrielle. So we have a point which is located in the centre of the source, scaled to the size of the source, and then we've got the run out represented by a line down to the bottom, which is sort of a compromise between mapping full polygons of the source and deposit. So this is how we would normally map landslides, because this is the sort of the technique where you get the most information about the landslides, where the material came from, how far it travelled downstream, and how many of these landslides, all joined up to this one deposit. And you get information on the area of the landslide, which we can then scale to estimate a volume. and we can look at like the widths and the length of the deposit. So we considered doing this for Cyclone Gabrielle, but it was just going to take far too long. So we ended up doing the points and lines, which I showed you just before.
You didn't map that face left of the cloud.
No, sorry, I didn't get round to that, but
Okay, cool.
yeah. Yeah, so sorry, there are a lot of slips in here that haven't been mapped. And I just actually want to say one other thing. This is the Earth scanner imagery that was taken after the event and after Cyclone Gabrielle, and it is not very good. But there was some areas there was 15 metres difference between points on the ground and where the imagery ended up. So it was not very useful for the landside mapping, as we really need to know in pretty good detail where those landslides are located. So this is what we're doing for Cyclone Gabrielle. Points scaled to the size of the landslide located in the middle of the source area, and then the debris trails, and we're also attributing the debris trails of whether they are primary, so they came from a main source, or whether they're coalescing, so they all join up together downstream. This is just an example. So that's the pre-event imagery, which we were using was Planet. That's what we had available for this area, and that's the post-event aerial photography. The landslides are pretty obvious there. Just a bit of a zoom in. So there's the points located in the centre of the source area, and we're using, we're colour coding them for different landslide types. So most of these are debris flows. There's a few slides and stuff in here. And then the debris trails. So has anyone got, I have no idea of the time, so someone sing out.
The question,
Yeah.
what's the real value in doing, just go back one slide, in classifying those into flows, slides, unclears or falls, when in Gabrielle, fundamentally, everything was wet and chances are most things were flowing anyway.
Yeah.
I wonder what the rationale was for having to go to that level of classification, because that takes time.
Yeah, it does. Yeah. So there's a new AI model out. It's a GPP model, so we can input the points with the landslide size, and different movement types have got different relationships in this model and can predict the downstream run out from the landslides. So I see your face, and at the moment what we're doing, because I'm not a believer either, but at the moment what we're doing is we're using the actual mapped landslides, and we've done a couple of catchments with polygons as well. So we're trying to verify whether this GPP model actually works, because I'm very skeptical. But yeah, so that's why. So we've got, so the slides tend to not go very fast. So that they tend to be, most of them initiate as slides and then they transition very rapidly into flows. But some of them, so these ones here, that just stayed as a slide, so it just sort of slid and it stopped. But the flows continue down into the stream channels, and then the sediment is delivered to the streams. Does that answer all right, Chris?
Yep. I've got many other questions.
Okay.
It's about 10 to tow, by the way.
How many?
It's about 10 minutes to tow the session.
But
10
oh,
minutes to go.
okay.
Does that help?
Okay, so I'm going to have to zoom up. Okay, so when you're mapping the landslides, this is what the aerial photography is really good for. You can actually see the source area here, and so I sort of can see those bare areas and then the deposit sort of overlaying the source areas. So I am going to have to zoom through. So there's the source areas, map the polygons, that's my interpretation of where the sources are, and then the debris overlying those source areas. Yeah, Yeah, and then I normally overlay them onto LiDAR so I can check that they make sense in the landscape, they're flowing downhill, and I can also see that there was other old landslides. This is pre-event imagery, so you can see there's old landslides were there already. So that gives me a clue that this is a really highly erodible landscape because this has happened before. So that's the slips laid over the LiDAR. This is the Sentinel 10-metre imagery. So I can't get much information out of that, apart from the fact that there was a landslide there. So this is LiDAR differencing is another way where we can map. We can figure out where landslides happened in the landscape. And this is just an example, Whareongonga in Gisborne. And you can see the blue areas are where there's been a positive change in the elevation of the land, and the yellow areas are where there's been a drop. So this has been the source, and then there's the deposit. And then there's the toe of the landslide, which has been eroded away by the sea. And then relic landslides. So these are landslides that have been in the landscape for a long time, possibly thousands of years. We don't know when they moved the last time, but looking at this landscape, you might not think there's many landslides there, but then you look at the LiDAR and I can see a lot of landslides. So those are the source areas, and then deposits, and there. And I think I might just leave it there, and I've got a little exercise for you guys to do to try and map some landslides out on some LiDAR. Yeah, so would that, if that would be useful?